and provide some key background information as well. While we're doing this, we'll also talk about some basic sequential excavation method tunneling principles and terminology. For those of you who aren't tunnelers or work extensively in the underground industry, there's a lot of terms and concepts that we use day in and day out, but they might be new to some of you. So we'll hopefully be able to inform you on some of those concepts. And then for about 15 minutes, we'll actually get to go on a tour. And that tour is basically a video presentation that we prepared as part of our committee initiative that will sort of take you, not live, but we'll have some video footage and you'll be able to see some of the tunnel under construction. And it also talks about some of the key challenges that the project had. And then lastly, because we did want to sort of bring this sort of a learning aspect to this presentation, we're going to talk about some key aspects of a fault crossing that the tunnel had to negotiate, both in design and construction. So there'll be a few slides about that, and then we'll wrap things up with Q&A, and hopefully we'll keep this under about 45 minutes. So just a quick introduction on myself. I have about 20 years of experience, most of that being in the tunnel and underground industry. Graduated from the University of Illinois with a bachelor's and master's of science. And most of my expertise is in tunnel and underground structure design, but I am a geotechnical engineer by training. So I do have experience with writing geotechnical reports, characterization, instrumentation, and also evaluating excavation impacts on adjacent structures. So as you all know, I'm also the current chair of the M.ASCE Geo-Institute Underground Engineering and Construction Technical Committee. Okay, so into our project here. The project is the Courthouse Commons Tunnel project located in downtown San Diego. And just to kind of give you the intent of the project is basically to provide access between an existing jail and new courthouse that was recently built in downtown San Diego. Currently, there is no tunnel. There is a lot of personnel that needs to be transferred from the two structures, and currently that's done by bus generally. So the purpose of the tunnel was basically to connect the two structures and to eliminate the extra mode of transportation to get personnel from one structure to the other. And then at the same time, because this block that the tunnel was going to pass underneath was slated for redevelopment, the tunnel would also allow that opportunity, allow the existing structure there to be demolished and then a new redeveloped structure built on top of it. So that was a key aspect of this project, which we'll talk about in a little bit. You can see sort of a 3D representation of the tunnel here in the lower left-hand corner, but it was a relatively shallow tunnel and not too big by tunneling standards, what I'm used to working with, but it did pass in very close proximity to what is the existing courthouse that is slated for demolition and redevelopment. So here's sort of another view you can see the various structures next to the alignment, and the tunnel basically in yellow here passing beneath what's termed the old jail and the old courthouse structure. So those structures were actually in use when the tunnel was being mined, and we had extensive instrumentation to monitor the effects of the excavation. Overall, very close proximity, and we did want to protect those structures, even though they were ultimately going to be slated for demolition. And in its place, there was basically going to be a mixed-use residential and commercial structure, and the tunnel would be constructed as part of that redevelopment. The contract arrangement was a design-build contract with basically the developer, Holland Partner Group, who we worked for as the designer, McMillen Jacobs, and we were, it's not strictly a design-build relationship because we were working for a developer, but it was like a design-build project because we were submitting our documents to the developer and the contractor at the same time. And the developer also had held the construction contract with the contractor. So here's a plan and profile of the tunnel. You can see in the center of this graphic, the tunnel was going to pass in very close proximity to the existing basement of the old jail and the old courthouse. I think the actual measurement is about 7 feet of the deepest foundation. It's about 300 feet long, the tunnel is. That's sloped to 100%. And at its biggest, the tunnel was going to be excavated to about 28 feet wide by 25 feet high, with a finished diameter of 15 by 10 feet. Again, it was relatively shallow, about 50 feet below the ground surface. And I mentioned the fault crossing or the fault before, where we passed beneath the fault or through the fault. We had a vaulted section that was included some specific design elements to accommodate future fault movement. It is an active fault. It's the San Diego fault, and we did have to design for the movement of that fault. So here the tunnel and cross section. There's a lot going on in these drawings, but there you can basically see the finished build out of the structure with ventilation duct above and walkway and clearance for both pedestrian or personnel and also small vehicles, electric vehicles to pass through the tunnel. It was a waterproof structure, so that's if you can see the red line around sort of the tunnel opening. It's basically had to be dry. There was a lot of specialized equipment that was going to be installed in this tunnel, from security cameras to a lot of other high-tech gadgets. So it was pretty important that the structure be stable, survive a fault, and also remain waterproof the entire time. So kind of a challenging design aspect to the tunnel. Geologically speaking, we were in a fairly inert area of San Diego, excavated primarily through this green unit, which is the old Paralick deposits, which is a sort of a marine terrace deposit overlain by alluvium. It's sort of classifies as a soil, but it's very stiff to stiff, consisting of silty sands to clays. It had enough clay in it that it was anticipated to be a good tunneling medium, meaning that it would stand up and not become unstable when it was basically opened up to atmospheric pressure. But one of the key drivers or requirements was that we had to dewater the alignment before we could start tunneling. You can see groundwater was close to 30 to 40 feet below ground surface, so right about at the tunnel center line. And we did have to go in and provide for some dewatering before we could advance the tunnel, which we were able to successfully do. So just sort of some background concepts on SEM tunneling, or also called NATM tunneling, or the Neuaustrian tunneling method. It's interesting in the tunneling world in that it's one of the few methods that we can sort of adjust and adapt on the fly, both in the excavation sequence and also the support requirements. That's a good thing where we're excavating tunnels that have varying geometries and also might encounter variable ground conditions where you may need to adapt the ground support or how you excavate the tunnel to basically minimize the amount of ground movements that you would experience, and also to protect structures around you. So there's a heavy reliance on careful controls and close scrutiny of the excavation process, and also incorporating real-time readings of instrumentation data in order to really understand the response of the ground and the structures around you as you're tunneling. So fairly unique in that aspect. Here's a few graphics of sort of the sequential excavation method, or how it was envisioned that the tunnel would be excavated. And that's basically with a top heading and a bench. So how this works is the top heading is sort of advanced first. We get upper crown of support in the ground, kind of protect ourselves with these pre-support spiles or canopy pipes out ahead of us to make sure the ground doesn't come in as we advance the top heading. And then once that top heading is in and the support is installed, then we can open up the bench of the excavation and complete the ring of the tunnel once the top heading is supported. There's a number of toolbox items that we allowed for, and it's typically done with these types of tunnels, and they can range from face bolts to pre-excavation grouting to sort of improve the ground if there's potential instability, drainage holes. If we hit pockets of water, we can install drain holes out ahead of the excavation to drain it. And then if the face becomes unstable, we can sort of leave, you can see a temporary wedge at the face of the excavation to help support it. And we can also apply sort of a flashcrete of shotcrete to help support that face wedge if needed. I mentioned pre-support. Here's just a few images of sort of what's entailed. On this particular project, we use both pipe spiles and canopy pipes. Basically due to the changing geometry of the tunnel and the fact that the bigger section of the tunnel was going to be driven from the shaft, and we had the laydown area and room in the shaft to actually install a long length of canopy pipes. They're about 100 feet long. Those sort of served as our pre-support for a good section of the tunnel, and then after that we provided pipe spile support, which is shown here in this yellow color in the graphic.
Tom, I'm so sorry to interrupt you. Your voice kind of cuts out every couple of words. I'm not sure if you're getting notifications on your computer, and that might be.
I'm not, but my screen just went blank, so hopefully that's not related.
Okay.
Let's see if we can get it come back up. Okay. I'm going to unshare. Sorry, I seem to be having technical difficulties. On my side, the screen is flashing. Good.
Did you want to try logging off and coming back in again?
Let me see if I can just close and reopen. Okay, that seems to help. Apologies. Okay, how's that?
Great, we can see it.
Okay. We'll keep moving forward and see if this continues to work. If not, I've got a headset I can plug in. So we'll just kind of quickly go through these next few slides and get to the video or the tunnel tour, hopefully here shortly. In terms of initial support, this is basically consists of shotcrete with structural support in the form of lattice girders. Sometimes they can be steel ring beams, but in this case, we went with lattice girders just given their lightweight and flexibility and ability to adapt to the conditions as we encounter them. They also facilitate a easier installation of our pre-support spiles that was anticipated later on in the tunnel drive. And you can see also the flashcrete I mentioned before was a sort of a pre-support method that is applied to the face of the excavation to help hold the ground up in areas where it does start to become unstable. So you can see that on pocket excavation, we didn't end up using this. We did use it on this project in areas where we encountered some face instability. And you can see the photo on the lower right-hand side, which basically to leave a face wedge at the face and sort of advance the heading in smaller pockets to hopefully help stabilize the ground and keep it from running away from us as the tunnel is. In the final lining, that's basically what the final structure is going to be comprised of. Here, it's a cast-in-place concrete liner, ranged from 10 to 18 inches thickness. And that basically is the final fit out of the structure. And you can see also, I mentioned earlier, we allowed for waterproofing. You can see in the middle photograph here, this is actual sheet we're using.
Tom, you've lost your audio again.
Okay. We'll try the headset. Okay, how's that?
It sounds great.
Okay, sorry about that, everybody. I mentioned the need for close monitoring of the excavation as the tunneling process is underway. And this graphic shows the extensive network of instruments that we had monitoring continuously while we were mining the tunnel. Everything in this middle block here was basically installed within the existing old courthouse and old jail. So we had to access those structures in order to read those instruments. So it wasn't easy, but there was available real estate, I guess, if you will, to get those installed, and we were able to monitor them pretty closely. So now we'll go ahead and start the tour. Hopefully, you all have a sort of an initial understanding of what's involved with the sequential excavation method, and we'll sort of let the video go here, and you guys can see how the tunnel was actually built.
The tunneling industry has many techniques for creating space underground. The most traditional form of tunneling, which was first performed thousands of years ago to create ancient Roman and Persian aqueducts, has evolved into what is now known as the Sequential Excavation method, or SEM tunneling. SEM tunneling is an observational method of tunneling that involves evaluating the type and behavior of the ground during excavation and determining the best combination of ground support components, a design-as-you-go approach. During tunnel design, the ground support is prescribed based on what is known of the ground from advanced geotechnical explorations. But the design also allows for additional measures and other support elements, known as toolbox items, which may be needed where ground conditions and behavior locally vary. SEM tunneling was recently applied on the Courthouse Commons Tunnel, which is a component of the downtown San Diego Courthouse Commons development project. The Courthouse Common Tunnel will provide pedestrian access between the Superior Courthouse of California and the Central Jail. The tunnel will be constructed in a congested urban corridor and in close proximity to existing structures, including beneath an existing jail facility. Close monitoring, detailed planning, and careful construction procedures are required to minimize impacts of construction on adjacent facilities, which need to remain operational during construction. Through most of its length, the proposed tunnel is approximately 26 feet in diameter, with a cross-section that looks like a modified horseshoe with rounded invert. The total length of the tunnel is about 328 feet, and at its nearest approach passes within 7 feet of the foundations of the existing jail. In addition to the challenges posed by urban construction, the tunnel will cross a known active fault that transects the eastern end of the tunnel and passes beneath the existing jail. The San Diego Fault is considered active and is designated as an Alquiste-Priolo earthquake fault zone. To accommodate design of the fault crossing, the designers utilized an innovative approach for the tunnel, which included over-excavation of the tunnel and backfill using a series of systematic seismic joints composed of compressible foam and gravel backfill to allow the structure to absorb anticipated ground displacements during a seismic event. The concept provides a level of ductility in the final structure and allows the tunnel lining to accommodate the movements, yet remain fully waterproof after displacement occurs. Prior to the start of tunneling, the groundwater was lowered to a depth below the tunnel alignment by drilling a series of wells and pumping out the water. Groundwater is maintained below the tunnel during construction because water destabilizes soils when they are excavated. Construction of the tunnel began with excavation of the starter shaft, excavated at the existing sidewalk adjacent to the central jail. The building side of the shaft is supported by a secant pile wall, and the remaining 3 sides are supported by soldier piles and wood lagging. The shaft required 3 levels of bracing and a reinforced concrete floor slab to withstand the central jail foundation and ground loads while limiting wall movement. Once the shaft floor slab was placed, the lowest bracing level was removed. Next, the flanges of soldier piles were cut in selected locations to provide room for canopy pipes, which creates a supportive arch over the tunnel. The first canopy pipe set is 100 feet long, with grout ports for annulus grouting spaced in pairs every 20 inches. When completed, the canopy pipes are left in place and filled with grout. The grout ports along the length of the pipes allow grout to permeate into any voids in the ground, further stabilizing the ground above the tunnel. The canopy pipes are commonly referred to as tunnel pre-support, since the pipes are put in place prior to excavating underneath them. Upon completion of the first canopy pipe array, the lagging boards between soldier piles in the window of the tunnel were removed, and temporary support consisting of a layer of shotcrete was added. After this support was in place, the soldier piles were cut out and a collar beam was installed around the tunnel opening, which is the final step before excavation of the tunnel could begin. The collar beam consists of a double-wide W section and an interior circumference matching that of the tunnel excavation line. Because of the size of the collar and access constraints through the shaft, the beam had to be lowered and installed in multiple pieces. Once installed, the collar beam provides a pathway for redistribution of forces vertically down through the shaft excavation support and around what is soon to become the tunnel opening. The collar beam was then encased in shotcrete. With canopy pipes and collar beam in place, the first round of excavation, known as the breakout, for the top heading could commence. The excavation started with an excavator-mounted hydraulic hoe ram, or breaker, to remove shotcrete and was followed by removal of soil. Excavation continued in this fashion until the next round of canopy pipes were installed. The top heading consists of approximately the top 3/4 of the tunnel cross-section. Excavating and installing support within a smaller opening reduces ground movement, which may impact overlying utilities and buildings. In a scenario where the ground becomes unstable or excess movements are detected by the monitoring system, the excavation can be broken into even smaller components. This process is known as pocket excavation. Once the top heading has been opened in each round of advance, immediate support must be put in place to control potential future ground movement. This is first achieved by applying a thin layer of shotcrete to all areas of exposed ground, referred to as flashcrete. The flashcrete creates a safe working condition for the crew to install the initial support. The initial support for the tunnel excavation consists of a lattice girder, which is installed for each 3-foot advance of the tunnel, and a minimum thickness of 10 inches of shotcrete along the entirety of the sidewalls, crown, and invert. The lattice girders are supplied in 6 sections that are bolted together to complete a full ring of the tunnel cross-section. 3 of the 6 sections were installed in the top heading as shown, while the remaining 3 will be installed to finish the ring during bench excavation. The shotcrete initial lining with embedded lattice girder creates a composite cylindrical shell of support to the ground around the excavation. The initial shotcrete lining is cured to an adequate compressive strength of approximately 75 to 100 psi. This usually takes 30 to 45 minutes, after which the crew can begin the next advance of the excavation. During this time, spoils, or muck, are removed from the tunnel via the shaft, using the track-mounted crane at the surface and 2.5 cubic yard muck boxes. The removal of muck is an important process to maintain tunnel production. When tunnel production is hampered by too much muck in the tunnel is said to be muck-bound. Once past the area of the canopy pipes, a different pre-support method began: pipe spiles. The installation and grouting of an array of 24 hollow pipe spiles, each measuring 12 feet long by 2 inches in diameter, became a required step in each excavation round. These pipes are much less stiff and therefore cannot carry the higher loads of the larger canopy pipes. However, since they are shorter, they more easily allow for changes in the tunnel alignment. They are drilled with a drilled jumbo using a smaller crew and are thus more economical. Excavation on the remaining 131 feet of tunnel was carried out in the same fashion and sequence as before the alignment beneath the canopy pipe arrays. After the top heading is excavated to the full length of the tunnel, the crew will excavate the bottom half of the tunnel, known as the bench. Removal of the bench will include installing the remaining 3 sections for each previously installed set of lattice girders, thereby forming a complete ring of structural support. The tunnel invert is then formed with shotcrete lining, which provides a structural connection to the shotcrete lining in the crown area, thereby providing a closed tunnel ring. In addition to the main tunnel excavation, 10-foot-high shallow niches of varying widths will be excavated on the south side of the tunnel in 4 locations. These niches will be used for utility and equipment storage. Once the entire tunnel cross-section is advanced from the shaft to the courthouse, the break-in will be performed. This operation requires removing a portion of the existing concrete basement wall of the courthouse to connect the basement with the tunnel. During the construction of tunnel projects, particularly in urban settings, it is important to ensure no damage is done to surrounding infrastructure. For the Courthouse Commons project, this includes roadways, various underground utilities, and multiple buildings, 2 of which the tunnel traversed directly beneath. To keep a close eye on the impacts of tunnel construction, a suite of geotechnical instrumentation was put in place to monitor movements in real time. Automatic total stations were used to continuously monitor installed prisms to measure locations of utilities, road services, building targets, and the tops of anchors set deep into the ground immediately above the tunnel. Furthermore, liquid level sensors were used on load-bearing columns of buildings. Piezometers measured the depth of groundwater that was lowered by the dewatering wells, and manual convergence monitoring of prism arrays set inside the tunnel was performed with each advance of the tunnel heading to ensure that movements of the tunnel support system are within estimated displacements. After the tunnel is excavated, a waterproofing membrane and a permanent cast-in-place concrete lining is installed to prevent water seepage into the final structure and to carry long-term ground loads acting on the tunnel. The permanent concrete lining also provides a smooth and flat walkway, walls, and ceiling and allows the tunnel to be fit out with utilities including power, lights, plumbing, ventilation, and electronic communication and security systems. To date, there have been 2 notable events that challenged the construction team during tunnel excavation. The first was fast-raveling ground. Unstable ground is an adverse condition for tunnel excavation since unstable ground can progressively extend beyond the limits of the excavation, increasing ground deformations and causing additional settlements at the surface, which may cause damage to buildings or utilities. At this location, the crown of the tunnel was a mere 7 feet below the bottom of a strip foundation for the building above. Despite the support of canopy pipes in this location, the tunnel excavation sequence was modified, and pocket excavation with flashcrete applied incrementally at the tunnel face was used to minimize the area of unsupported ground and better control ground movements. Additionally, the application of sodium silicate was used on the exposed sandy ground. Sodium silicate reacts with the soil to form a crust of lightly cemented material that not only stands up long enough for flashcrete to be applied, but also helps prevent soil erosion from the pressure of the shotcrete being applied. The second challenge presented itself just beyond the tunnel breakout from the shaft. While drilling the canopy pipe array, 2 pipes encountered brick. The canopy pipes were eventually drilled through the brick, and tunnel excavation resumed while soil samples were analyzed for contaminants. Once the excavation had advanced to within 15 feet of the observed brick location, probe holes were drilled to investigate the size and location of this brick anomaly, and more soil samples were tested. This anomaly was suspected to be a decommissioned brick-lined well turned into a trash pit, a feature known to exist in downtown San Diego from previous excavations. The major concern was that the pit contained loosely compacted materials with significant voids that would collapse into the tunnel once the brick lining was removed, causing an uncontrolled chimney behavior up to and under the building foundations above. After a review of inferred geometry of the brick anomaly, a grouting campaign was initiated. Holes were drilled and a grout mixture was injected to fill the voids and stabilize the materials inside the trash pit. Meanwhile, test results of soil samples indicated high amounts of lead and other metals, as well as trace amounts of organic vapors and other potentially hazardous materials. Additional probe holes cased with perforated pipe were drilled into the brick anomaly to further define its extent and then be used for grouting. A total of 302 cubic feet of cement grout was injected. When the grout was adequately set, excavation continued, and additional precautions were taken when removing the contaminated ground encapsulated by the brick structure and consolidated with grout. Upon removal, it was confirmed that the brick structure was an abandoned 19th century well backfilled with broken glass and porcelain, metal pieces, and burnt material. This concludes the virtual tunnel tour of the Courthouse Commons Tunnel Project. We hope that you enjoyed the tour and that you were able to see firsthand some of the challenges and unique aspects of this project, as well as to learn about the fundamentals of the sequential excavation method of tunneling. For additional information on the tunneling and underground industry, including academic scholarships and career opportunities, please visit www.undergroundcareers.org. We would like to thank the organizations that helped create this virtual tunnel tour, including the Courthouse Commons Tunnel Project Team, Holland Partner Group, Atkinson Construction, McMillen Jacobs Associates, and the County of San Diego. Funding for this project was made available by the M.ASCE Geo-Institute and the UCA of SME.
I hope you were able to see and hear all of that. I could, so that's kind of tour in a nutshell. Let's see if I can get back to the presentation here. So I mentioned we were going to spend a few slides talking about the fault crossing. Since we're running a little low on time, I think we'll go through these pretty quickly and leave questions for the end so that we have enough time to have a conversation about the project and the video tour. So the fault crossing was mentioned before. The San Diego fault is an active fault, and we were anticipating 15 inches of movement across the fault and across the tunnel. You can see in the graphic that it was a well-known fault and had been investigated extensively. Unfortunately, we couldn't really investigate it right at the vicinity of the tunnel because of the buildings that were above. But you can see an effort was made, and we actually did get some good mapping and information from it. In terms of the seismic design, the video on the previous slides mentioned the seismic fault being an oversized structure to allow for potential fault displacement. How that was accomplished was basically through a series of seismic joints installed at 10-foot spacing and the inclusion of a compressible backfill behind the final cast-in-place concrete structure, with the idea being basically that the compressible material would be allowed to fail during a rupture event, and the joints would have some ductility and allow for movement between structures so that strains in the concrete were exceeded, and also so that we could maintain water tightness with the waterproof membrane. I'll show detail of that in a second, but we modeled this fairly extensively. I won't go into the nuts and bolts on the 3D model, but we did look at various foam stiffnesses, joint widths, sort of optimize the configuration. So we did quite a bit of study that could merit its own presentation in the future. But some details on the seismic joint was basically, I mentioned the compressible foam, which you can see as sort of the honeycomb pattern hatch section on the right-hand side. And that's basically behind the cast-in-place concrete. And then at each joint, we also include that compressible foam, but the waterproof membrane receives a fold, so it allows the membrane to basically extend and not fail in the event we experience some shear displacement between that joint. And then sort of as a last ditch effort, the joint actually receives a flexible seal at the surface. We call it the intrados, or the inside surface of the cast in place final liner. So sort of a two-tiered approach to keeping this structure waterproof, but also maintain its structural integrity so that it can remain serviceable after seismic. Just a few photographs and graphics of what we actually encountered when we were mining through the fault. We actually uncovered what believed to be the main trace of the active fault, but then a few smaller splays, which you can see in the graphic with lines being the various fault features that we encountered. The main fault is shown here in the center photograph, and that's basically a photograph of a person standing in the tunnel but turned 90 degrees. So we're looking at the sidewall, and at the lower portion of the excavation, the bench, and that's the fault, sort of a high angle 85-degree fault coming across, basically intersecting through the entire tunnel at an oblique angle. So we saw evidence of it. We got good mapping information from the fault, and basically confirmed that our design assumptions were valid, and we didn't have to make any changes to the design approach, which was a good thing. So with that, I'll go ahead and wrap it up, and we'll take questions now, hopefully for a few minutes. We have some time for that, and thank you all again for your time and attention.
Okay, thank you so much, Tom. We had a question asking about the specific design elements for the fault section, but you've been over that. So let's move on to, there was another question asking if this video is on YouTube. We will be posting this very presentation, so you'll be able to see the video that way. And then this is something you and I can discuss later if this is something the Underground Engineering Committee would like to post as a standalone. That's something we can discuss later.
That sounds great.
Okay, we have a question about how does the SEM tunneling method compare to other methods? For example, doing heavy geotechnical analysis and design and sticking to one method of construction rather than a sequential method. What's more cost effective?
These are good questions. And I think the end of the video really illustrates why SEM was advantageous and arguably probably the best method to excavate this tunnel. Generally for SEM tunnels, they do tend to be more expensive and slower. But for short drives like this one was, a 300-foot long tunnel, they can be economical because the cost and time involved with mobilizing heavy equipment, a tunnel boring machine, or something similar, really favors an SEM type approach. And like I said earlier, the SEM method can be adapted. And in this case, in this project, it sort of had to be when we encountered this unknown and undocumented well structure beneath the existing courthouse basement. If we had hit that with a machine or a tunnel boring machine, depending on its composition, we might not have been able to get through it, or at least might have had to spend a lot of time trying to remove that obstruction before we could continue excavation. And with those types of machines, the access is very limited. So you don't have the full access to the face that you do with the SEM method. So again, another good reason to use SEM is to be able to adapt to changing conditions, but also undocumented or unknown conditions. So overall, a pretty good attribute for this type of approach.
I'm not quite sure about the question, but as well as, I'm guessing this means reliability for future problems, or perhaps being able to anticipate or future problems?
Sure. In terms of reliability, I think you could make an argument that, there are other methods that may be more reliable. Sometimes in these types of tunnels, SEM tunnels, shotcrete durability can be a concern. But in this case, it wasn't really for us because we were putting in a cast in place final liner, and we felt pretty confident that proper QA, QC procedures could be followed, and it's been done before. So we had a high degree of confidence in the method. In terms of other tunneling methods that would prove reliable. Definitely a tunnel boring machine with a precast concrete segmental lining behind it. There's a level of reliability with that type of approach that, I think would rival an SEM approach. But again, at the end of the day, for this particular project, it was really the geometry and the length that sort of drove the decision and, allowed for the SEM method to be cost competitive and advantageous.
Okay, we have a question about safety concerns. Are there major safety concerns with SEM versus other methods, pros and cons?
For sure. There's definitely safety concerns with SEM methods because, generally you're working at an open face, whereas with some mechanized tunneling methods, that face is protected with a cutter head or some other method that, personnel don't need to go up and access frequently to work at the face, to install support. So a lot of that can protect the workers with a mechanized tunneling approach. So definitely safety is a consideration, but if done right and properly planned, those potential safety issues can be addressed with, I mentioned the toolbox items before, for when the ground or a condition doesn't appear to be as anticipated, the method can be adapted to provide a more stable opening and ultimately a safer opening if needed.
Okay, on YouTube, we have a question from Aomar Ben-Slimane, and I'm sorry if I did not pronounce that correctly. Amazing pictures of the fault. Any water tunnel inflow issues?
No, we do. We actually had provisions in the contract for drainage. If we did encounter groundwater that wasn't dewatered or a pocket that the systematic dewatering system didn't mitigate, we had provisions to deal with that. Fortunately, that wasn't an issue, and we were able to keep the groundwater largely below the invert of the excavation the entire time. So that was a very good, a very critical aspect to this approach. Is anytime we encounter groundwater in this type of excavation in effectively soil, it can prove to be problematic and lead to instabilities and potentially greater ground movements and impacts to the structures around us.
Any follow-up on the more extensive use of Packer test data for major tunneling projects and the use of Raymer equations?
We did not, I don't believe we conducted any Packer tests for this project. Typically, we see those done for our harder rock tunnels or rock tunnels. I wouldn't necessarily classify this as a rock tunnel because it was kind of in a cemented soil or a very dense soil. But definitely those are aspects of tunneling that we want to consider and should consider where we're working close to the groundwater table or below it. But here, we didn't need to make any of those predictions because we were confident that the dewatering system would basically make the groundwater problem go away and keep it below the excavation so that it was never really encountered, and we didn't have to plan for groundwater inflows or predict inflows into the tunnel excavation. And
then one more quick question, if we may. You mentioned encountering the garbage pit. How often does that come up in urban tunneling, especially in places that have been settled for a long time?
It's the first time I've ever seen a garbage pit encountered, but working in the underground for 20 years, I think we've seen a lot of unusual items unearthed or uncovered. I think here in San Francisco at one point they encountered a buried ship from over several hundred years old, and it turned into an archaeological site as a result. But I've heard rumors of whole locomotives being encountered in Seattle, and it's just the list goes on and on. But definitely, it speaks to the need to do your homework and do your investigations to the greatest extent possible, because when those things are encountered in a tunnel, they can be problematic and expensive and difficult to deal with. Fortunately, with this instance in the well, it was fairly minor, and we were able to get past it without too much issue. But yeah, those kind of things need to be studied in depth and planned for.
Okay, unfortunately, it looks like our time is up. We have a comment thanking you for your presentation and saying it was great, and I think many others of us agree. Thank you so much for the video and for coming to talk to us on today's Lunch and Learn.
Great. Thank you, everyone.